Very good morning to all of you. Today we will be having practical number 1. The aim of this practical is to conduct a test on Pelton turbine, it's an impulse turbine, under various speeds, loads, and to plot the main and operating characteristic curves. Pelton turbine is a high head turbine. It's an impulse type of the turbine. We call it as an impulse turbine since the jet of water striking the bucket with a very high velocity, and according to your Newton's law of motion, the force will be exerted by the jet. Here, the Pelton turbine is a high head turbine and it's a free jet turbine. This means the runner is rotating in an atmospheric pressure. Pressure everywhere, that is the jet when strikes the bucket or after striking the bucket, is always in atmospheric pressure. And this is why it is called the free jet turbine. Mostly, the water is stored in the dam. As shown in this figure, the water which is stored in the dam is allowed to enter into this penstock. At the end of the penstock, the nozzle is fitted. Here, the potential energy of a hydraulic water that is stored in a dam is converted into kinetic energy when it moves through a penstock. And then while coming out from the nozzle, this kinetic energy is very high, and the high kinetic energy jet is allowed to impinge over the buckets. The buckets are generally hemispherical in shape with a splitter at its middle section. As it strikes over the bucket, the runner starts rotating. Here the casing is provided, but the casing doesn't provide any specific hydraulic function since the pressure everywhere is a atmospheric pressure. The provision of casing is made only to avoid the splashing of water. So thus, the water energy is converted into the mechanical energy using Pelton field. Remember, this is high head turbine and the turbine is having a very low specific speed. Mostly this section where there is a nozzle, here you can observe that this is what a spear rod fitted at the center of the nozzle, and this spear rod end is connected to a governor wheel. And the function of this spear rod is to regulate the flow quantity of water towards the Pelton turbine. If we move this spear rod inside the nozzle, the cross-sectional area will reduce and this will reduce the discharge. Yes, of course, knowing the continuity equation, you will easily identify that decrease in area will decrease the discharge. And this happens when suddenly the load on the turbine is decreased and the speed of the turbine is increasing. That time we need to supply a small quantity of water. But when there is a very high load on the turbine, we need to supply higher quantity of water. In that case, the nozzle spear rod inside this nozzle will move back. This will increase the area and increase the discharge towards the turbine. So simple nozzle control governing is employed in this turbine. This is what a nozzle control governing, which is elaborated in this figure diagram. This is what a cross-sectional nozzle, the this spear rod is there. If it is moving in forward direction, the discharge will decrease. If it is moving in a reverse direction back, then the discharge will increase. That's a simple nozzle control governing is used. The governing is the mechanism that generally provided with all type of the turbine so that the turbine can run at a constant speed. The constant speed is needed for a generation of 50 hertz frequency electrical energy. And we need to run the turbine alternator say TSA to be at constant speed. And hence it is necessary to have a nozzle control governing arrangement. The buckets, these are provided on the periphery of the runner. The bucket attached to the runner, those are having a bowl shape or we call it a hemispherical shape. These are symmetrical in shape and these buckets are arranged in such a way that the jet of water after striking the bucket at its center gets splinted into two different directions and this will be deflected by an angle of 160 to 170 degree as we discuss all this during your theory lectures. Casing, it doesn't have any specific hydraulic function. The provision is made only for avoiding splashing of water. Casing will have definitely a very important hydraulic function, but in the case of reaction turbine and not in the case of impulse turbine. Pelton is an impulse turbine. Braking jet. This braking jet is provided generally because whenever there is a need to decrease the speed of the turbine or whenever there is a need to stop the turbine runner, the runner cannot be suddenly stopped because of its momentum and mass, and that's why the braking jet is provided in such a way that this jet will have impact at the back of the bucket, and after having an impact at the back of the bucket, the runner speed can be reduced. So that is what the braking jet. The important terms is very simple. The level of water inside the tank and the consider the level of your tail race. This height we called it as a gross height. But obviously, when the water is moving from the dam to the your penstock, from the penstock into the nozzle into the your Pelton wheel, and then again coming to the tail rest. So this involves head loss in friction. So due to head loss in friction, there is a reduction in head. The effective head available may not be equal to your gross head, and that effective head is known as the net head. So gross head is the total head, and net head is the head once we subtract the head loss in friction. Obviously, we can calculate this head loss in friction by a simple Darcy's equations, 4FL v square upon twice GD, that you learn in the second year fundamentals of fluid mechanics, that we can use to obtain the net head. Remember, the number of buckets in Pelton wheel can be estimated by a simple correlation, which is 15 plus capital D upon 2D. Capital D upon D is called as a jet ratio. It has a very high significance in your Pelton turbine because this decides that what should be the diameter of the runner, and larger diameter of runner is not good for us because larger diameter of runner will result into a very large momentum. Again, the small d is the jet diameter. The diameter of the jet will be very small when we need to have very high kinetic energy. If the diameter of jet is very small, the jet ratio increase to a very high value. That is also not needed. So simply having some optimization on these two by conducting various experiments, uh, the simple correlation was developed, and this is 15 plus capital D upon 2D. With this equation, we can obtain the number of buckets. Remember, larger size of diameter of a runner will always good because that can have a larger spacing of bucket. But remember, if the diameter of runner is very small, then the spacing between the bucket will go on decreasing. And it may happen that after striking one of the bucket, the jet will try to strike or interfere the path of the incoming bucket. So that is why this jet ratio is really important to consider. Power extraction, if the wheels of the buckets are stationary, means the buckets are not moving or the runner is not rotating, then the power will be zero, obviously, because to have power there must be some force acting over the bucket and there must be some displacement. But if the wheels are rotating at the same speed, suppose, that is the velocity of the jet and the peripheral velocity of the runner, if they are same, then again there is no any power extraction. So that's why it is always important that there should be some relation between the inlet velocity and peripheral velocity. Of course, the efficiency of the Pelton turbine is very high. Simply by derivation, we already proved that if the peripheral speed is half of the inlet velocity of a jet, then definitely the power extraction will be very high or at its maximum capacity. There are three different types of efficiencies involved in this type of turbine analysis, that is Pelton analysis or maybe a reaction analysis. Hydraulic efficiency, mechanical efficiency, and overall efficiency. Hydraulic efficiency, we define it as a runner power upon water power. Water power means what? The power which is available inside the dam. And runner power means what? After having a loss of friction in penstock and nozzle, and the inlet kinetic energy is allowed to impinge over the blades of the Pelton turbine, and the power which is available at the bucket or the runner of that turbine, we call it as the runner power. Obviously, any mechanical system is always needed to be installed with some mechanical components. So there are many number of bearings are involved. There are many number of directly rotating or maybe a stationary parts where there is a larger amount of friction. And because of this, the runner power may be 10 kilowatts. For example, it is a 10 kilowatt, will not be available as a shaft power output. It may be 8 kilowatts. Somewhere 2 kilowatt is we are missing because of the losses, frictional losses, or purely mechanical losses. So if I want to consider these losses, then the mechanical efficiency is defined as shaft power upon runner power. See, there are now three different powers: water power, runner power, and shaft power. Water power is the power which is available inside the tank. Runner power is the power which is available inside the runner, and shaft power after transmission of the runner power to the shaft of the turbine. We call it as a shaft power. So these are three different powers actually. The overall efficiency means what? The output is the shaft power and the input is the water power. So if I take the ratio of the output to the input, considering the entire power plant, then that efficiency is referred as a overall efficiency. Obviously, overall efficiency must be the product of hydraulic efficiency and mechanical efficiency. So that's all about a small theoretical introduction for this Pelton turbine. Now, before the starting of this, our Pelton turbine trial, it's a virtual trial, obviously, but I need to verify, or we must have to know some fundamentals. So for this, you must have to attend this simple test. That this test you can conduct at any moment. Rightly, now I'm only explaining that what is the questions of this test and what is their answer. Suppose there is a turbine, obviously a Pelton turbine governor. This turbine governor, I am writing these three different sentences, and you have to find out that which of these statements are correct. First, helps in starting and shutting down the turbine unit. Second, controls the speed of the turbine set to match it with the hydroelectric system. And third one is a sets the amount of load which a turbine unit has to carry. So which are these statements are correct? Are all three correct? Or only one and two correct? Or only two and three correct? Or only one and three is correct? So the answer must be what? Obviously, it controls the speed. Governor always controls the speed. So where there is a two involved, that must be the option. So one and three cannot be. So two is involved here in all three. Does the turbine sets the amount of load? Governor set the amount of load which a turbine unit has to carry. Just think it over and find out whether it is possible or not. Try. I'm waiting for 1 or 2 minutes. Coming back, which is the correct answer? 1 and 2 is the correct answer. Means it helps in starting and shutting down the turbo unit, and most important, it controls the speed of the turbine, say, to match it with the hydroelectric system. Okay, the second question, the deflector of Pelton wheel. See, I discussed many things about this Pelton turbine, but I did not talk about deflector. What does it mean? This means I am expecting that you must be able to remember your theory hours of learning this Pelton turbine. Remembering that theory hours, tell me that the deflector of Pelton wheel, what it ensures. Does it ensure that buckets receive the full jet impact? Does it avoid wastage of water during the change of load? Does it reduce water hammer hits? Does it diffuse the jet into the whirling mass? The correct answer is yes. Yes, this is what a correct answer. Reduce water hammer head in penstock. Remember why we are providing the deflector. Many times, suppose if the load on the turbine is decreased suddenly, what will happen? The turbine rotor will start running at a very higher speed, and that we don't want because generator must have to produce the electricity at a constant frequency of 50 hertz, and that needs a synchronization and constant speed. So turbine, I must have to reduce the turbine speed. And how it is possible? By decreasing the discharge moving towards the bucket. How I can decrease the discharge? Yes, simply by nozzle control governing. We will allow the spear rod to move inside the nozzle and reduce the cross-sectional area. This will reduce the discharge. But when we are doing so, what will happen? The water which is already present inside the penstock and running towards the turbine will suddenly stop. And this sudden stoppage of the water inside the penstock will lead to very high rise of pressure that forms the pressure pulses. And it strikes over the surface of the penstock, and that there may be a chance of mechanical damage or maybe a very accident can happen. So this we call as a water hammer effect. So sudden movement of your spear rod inside the nozzle will always lead to have water hammer effect inside the penstock, and we have to have a control over this water hammer effect, and that's why what we do, we always provide a deflector that also moves with the nozzle. So before the nozzle come into a full action, this deflector, what the deflector will do? Deflector will only deflect the jet, and this will not allow the jet to strike over the bucket, and the jet is directly diverted towards the tail race without striking the bucket. So this ultimately reduces the speed of the turbine slowly before your nozzle come into the action. The deflector does his job, and that's why we always provide a deflector with the Pelton wheel. Another question, consider the following energies associated with the Pelton turbine. That's mechanical energy, kinetic energy, and potential energy. Now the job is that you have to arrange the sequence, that in what sequence there is an energy conversion in the Pelton turbine. Read it. For a moment, I will stop. Okay, I think now you are ready with your answer. Just verify. First, water is there inside the dam, so it will possess potential energy. Then water will move through this penstock and the nozzle. So there is a conversion of this potential energy into kinetic energy. The high kinetic energy jet is then allowed to impact over the blades or the buckets of the Pelton wheel that rotates the runner, and mechanical energy in the form of rotation of shaft is available as output. Thus, the correct sequence is 3, 2, 1. So the answer is C. Great. Next question is saving of work done and power by fitting an air vessel to double acting reciprocating pump is of the order of saving of work done and power by fitting an air vessel to double acting reciprocating pump is of the order of running at unit speed, working under unit head, or when it consumes a unit discharge, or when it geometrically similar to the specific turbine. I'm giving you the correct answer, but you have to think on it again and try to come up with the appropriate theory read. The answer is working under unit head. Here, you must have to read the book of fluid mechanics or fluid machines, and here you have to find out first reciprocating pump, its working, construction, and the what is mean by air vessels. Mostly air vessels are always fitted with the pulsating type of the flow. So why they are fitted, how it works, how it saves the work done and power, that you have to read it first, and that is why I added this question purposely. I know this question is not related with Pelton turbine, but definitely remember when there is a pulsation flow, we need to use a air vessel. Either it should be a turbo machine or it may be a positive displacement machines. Let's consider another question. Here I have given some examples of the turbine. That's a bulb turbine, Francis turbine, Kaplan turbine, and Pelton turbine. And you have to arrange these turbine in a decreasing sequence, that is from high to low. So in a decreasing sequence, you have to arrange for the heads acting over the turbine. As we started with the practical with a single sentence that Pelton turbine is a high head turbine. So first must be a Pelton. Thereafter, Francis is medium head turbine. Then another turbine is a bulk turbine. And then Kaplan turbine, which is the turbine that works under a very low head. So in decreasing order, the correct answer is 4, 2, 3, 1. That's what simple questionnaire that we should know before performing this test or practice. Let us see how we are going to conduct this test. This is a simple virtual lab test. You know that it's a COVID-19 situations, but one should not stop with this COVID-19. So we are going to continue our practical using this virtual lab. I am very, very, very thankful to MHRD government of India. They have taken the initiatives results into a fantastic development of these websites that allows us to conduct the practicals in a virtual manner, and that's what I'm really thankful to this. I take this opportunity to thank this virtual lab MHRD government initiatives. Referring to this, let us consider that in what sequence I am going to conduct, or we all are going to conduct this practical. You may practice it at home also. Whenever you are having a free time, you can go on conducting your own test and come up with your own solution. Doesn't mind. Here I am only giving you a guidance. You may come up with your many number of solutions by selecting various heads, and you may conduct a trial. So here remember, this is what the sequence. You must have to remember that what is mean by impulse turbine, what is mean by reaction turbine, what is mean by gross head, and what is mean by net head before the start of or conduct of this trial. The stage one, you have to switch on the setup. How you can switch on? Here, it's a main switch. You just have to push the green button. Once you start, the pump will start. Here is a water pump and here is a Pelton turbine. Why water pump is there? We don't have any arrangement of hydraulic dam, civil construction dam. So there is no head which is available that will act at the inlet of the turbine. So this work we are going to do with the help of this simple pump. The pump will pressurize the water and will allow the pressurized water to enter into the Pelton turbine. This means the pressure is definitely equal to the head available over the turbine that you can select here. You can select any type of the head. There are 3 to 5 choices. Select any one that you want and click OK. Once you click the OK, second step will appear. Now, just move this wall, open this wall. Once you open this wall, the water flow rate will go on increasing, and this will show the pressure over this pressure gauge. As you go on opening the wall, there is a pressure shown by the pressure gauge. Remember, if you select the head of the water 17.5 here, the equivalent pressure will be displayed here as a 2.27 kg per cm square. This means bar. How? That's your fundamental knowledge. Pressure P is always equal to rho GH, where rho is density, G is 9.81, acceleration in meter per second square, and H is head acting over the or head of the water column. You can calculate the water column pressure. Remember, you must know the fundamentals of gauge pressure and absolute pressure. I'm not going to tell you that how this value 2.27 comes. It's your job that you must have to find out that what will be the equivalent head and equivalent pressure. That's all. Once you finish this, just click on the next button. You will appear with the next virtual video. Here, this is what a drum which is attached to the turbine shaft. You learn in your theory of machines how to measure the brake power or shaft power. This we generally do by using a dynamometer. A rope brake dynamometer is generally used. Here, that's what a dynamometer provided with this rope. One end of the rope is provided with a load, and one end of the rope is provided with a spring balance. So I will have a reading of W, I will have a reading of S, and from this center point to this is the effective radius of a drum that includes the drum radius as well as the rope diameter. So the effective radius of this setup is 0.15 meter. So the torque acting over the shaft is what? Load which is placed here. S, that is a spring balance reading. So W minus S into R. This will be in a W minus S into R. This will be in kg actually, but you must have to convert it into the Newton. So multiply it by again 9.81. Substitute the value of W 1.8 kg, S as a 0.7 kg. Just an example which is given. When you are conducting the practical, the readings may be something different, and then calculate the torque, which is the product of W minus S into R into G. In the next stage, you just have to monitor the speed, read the speed that the tachometer is showing to you. The speed is available. Just go on clicking next. You will provided with this number of slides. Here now we have to measure the discharge. I know the discharge, how we can measure the discharge? Simply using Venturi meter. I can measure the discharge simply by using a simple equation of 8 by 15 CD under root 2G tan theta by 2 into H raised to 5 by 2. Where CD is the coefficient of discharge and it is generally constant, and here it is 0.6. Theta is the angle of your measurement. H is the height about the or level difference of water, initial reading and final reading. That level difference is H. Substitute the values, you will obtain the discharge. Then you have to have these observations: 50% gate opening. These are all we have said in the previous slides. We already said all these. Now your job is what? From these observations, you have to calculate this. Like input power, output power, efficiency, unit power, unit speed, unit discharge. When you will run the simulation, you will come to know that when you are selecting this input power, the formula is given, everything is given. You just have to find out that which value is expected here in this formula and what is your observations. Go on adding this, do the calculations on your own calculator, add your answer. If your answer is okay, then you will allow to move to calculate output power. Again, do your same procedure. If your answer is okay, you will allow to do to find out the efficiency. In this sequence, you go on calculating your results like this. All these answers are available. Once you finish, just click in the next slide. You will move towards the next slide. So again, you can repeat the observations. You can repeat your observation as many times as you want. How we can repeat the observations? Go on adding the load. Initially, what we added, suppose initially we added only 1.8 kg. Then go on adding 2 kg, 2.4 kg, 2.6 kg or 8 kg. Go on adding the load. So once you go on adding the load, torque will go on increasing, the brake power will go on increasing, and you will able to find out the performance at various load conditions when the most important head acting over the turbine is constant. So this way we will go on conducting the test and we will come up with the output curves. Three different curves you will have: efficiency versus unit speed, unit power versus unit speed, and unit discharge versus unit speed. Come up with this solution. That is what your outcome of this experiment when we maintain the speed of the head of the turbine cost. The similar trial we will able to conduct, but in that trial we will not maintain the head as a constant. We will maintain speed as a constant. In previous trial, what we did, we maintain head constant and speed goes on varying. But here in this trial, we will maintain speed as a constant and we will go on varying the head. Suppose if we add the load on the turbine, the speed will decrease. We will not allow. What we will do, we will open the valve again, increase the discharge towards the turbine, and again obtain the same speed which is set for your first reading. Go on doing this, try to maintain your speed constant and repeat the entire procedure what we did in the above. We have to go on repeating the same procedure of measurements, then calculation, and then again the curves. So this will be what our sequence of operation. Now let us actually perform the simulation. I will go on performing one simulation. Your job is to perform many number of simulations, come up with your number of readings, come up with your own answers and submit those answers to me at earliest. Okay. I am just showing you one sample. You will have to repeat it at home. As per your convenience, please repeat it at home. The link is provided in your lab manual also. Even I have provided this link which is visible to you directly here, or I will put this copy, I will copy this link and will put it to you on your maybe a WhatsApp group chat, or maybe in your classroom I will put this link. Hmm? So let us perform for constant here. So that's what the simulation. Try to observe very precisely. This is what our setup. I hope here the picture of his own, your own. This is what a pump. We selected a pump because we don't have a hydraulic dam here. So we created the pressure head using this centrifugal water pump. This is what a Pelton turbine setup. This is what a shaft, the central circle is the shaft of the Pelton turbine. This is what the drum attached to the shaft of the Pelton turbine. This is what rope dynamometer drum. The rope is wound over the dynamometer. One end of the rope load is attached and one end of the rope spring balance is attached. This is what the pressure gauge. The water which is coming through this pump will enter through this penstock and then it enters into the Pelton turbine. At the end of this penstock, nozzle is fitted that creates a jet of water and the jet is allowed to impinge over the blades of the turbine. The tank which is provided at the bottom of this Pelton turbine is just a collecting tank, water collection tank, and the water is again recirculated back to this tank of the pump. So water will be recirculated continually. So this is what a simple test of the Pelton turbine. Let's move on to the next simulation. Now, what we have to do, we have to start the pump. Let us start the pump. The pump is rotating. I know the voice is not available, but the pump is now running. You can select the head. Any head, what you want, you can select. Let us consider 16.5 is the head. Press OK. So I selected a head of 16.5 meter. Now, open the wall. This way I open the wall. Okay, now what is the constant pressure? 2.53 bar kg per cm square. Why? Because we selected head equal to 16.5. How it comes? 16.5 is your head. So P equal to rho G H 1000 into 9.81 into 16.5. Find out the answer. You will find out the answer is in Pascal, that is Newton meter per meter square, but Newton per meter square, that is a Pascal. But remember, you have to convert it into the bar first, and that answer is what? 2.53. I will not show you how to calculate the pressure because you must know this fundamental principle. So now you are having these readings. Load which is added to the pan is 1.8 kg. Spring balance reading is 0.8 kg. The radius of the brake drum is 0.15. What will be the torque? What will be the torque? If you move on this cursor at this location, now you will have this equation. Just put these values in this equation. W minus S into R into G. So 1.8 minus zero point 0.8 is 1 into 0.15 is 0.15 into 9.81. So you put your answer here. Remember, unless and until you put your answer here, you will not able to move further. So you must have to do the calculation on your calculator and put the answer here. For flexibility, I will do this calculation in Excel sheet and then we'll put this in here. So 0.8 to 0.15. The answer is 117.72 Newton meter. 0.8 into 0.15. Most given. It's 1.15. Maybe it's taking a kilonewton meter. So it's taking 1.47 Newton meter. Observe the speed. It is 1100 RPM now. The turbine is running at 1100 RPM. That you can measure with a simple tachometer or simply speedometer is attached with the device generally and that directly shows the reading of this speed. Now what we have to calculate, we have to find out the discharge first. So set this initial reading and final reading. So that's what a change of level of water. Now this is what the readings which are available. The head of water is 8.6 centimeter. Now I have to calculate the discharge. So we will calculate the discharge using this formula 8 by 15 CD. CD is taken as a zero point 0.6 variables in the calculation. Zero point 0.6 theta is the 90-degree angle. The angle made by the sensor with the water level is 90 degree. 8 by 15.6. I have to do the calculations on 0.6 on the road 2G. 0.0498. So here let us put the answer. That is what 0.0031 meter cube per second. This is what the discharge. Once your answer is correct, then and then you will able to move in a next slide. So now these are observations. Gate opening is 50%. Specific weight of water is 9810. Discharge is this. Constant height 16.5. Speed of motor 1100 rpm. Torque is acting on this. So input power is gamma QH. Gamma is 9.9810. Q we know that point double zero 0.0031, and head acting is the 16.5. Just calculate this and put here in 9810 0031. Its turbine is developing 501.78 watt. Sorry, water power is the turbine is the one. That is your answer. Now output power. That we can calculate 2 pi nt upon 60. Simple brake power equation. It is 1100. Torque acting over the turbine is 1.47 Newton meter. So 169.4 is the answer. We will put here 169.4 watt. Take the answer correct. Calculate efficiency, output power upon input power. The answer is 33.76%. Pick your answer. Answer is correct. Unit power is output power upon root of h cube. Answer is 2.53. So we'll put here. Pick your answer. Okay. by root h is the unit speed. The discharge is q upon root h cubed. So this way, these are all results which is available for this Pelton wheel trial. Click on next button. Again, you will land on the trial number 2. That's what trial number 1 we finished. Now increase the load. Just click on this hand. Now the load is added. The load in the pan is now 2.8 kg. Spring balance reading is 1.4 kg. Again, go on continuing this entire practical and come up with your solution. So we'll fastly move. So we have to calculate torque first. Torque is 2.8 minus 1.4. Pelton turbine is a type of impulse turbine. You must have to answer these questions in between, then and then next slide will open. This way it is open now. Measure the speed. Speed is 930. Now observe the speed. Previously the speed was 1100 rpm, but now the speed is 930 rpm because we added a load in the pan. We added a load over the turbine. That's why speed is now decreased. Just adjust this height of level of water. So the discharge is now, you can calculate the discharge. So H is now, remaining will remain same. H is now 8.6. So question is arise, head of water is calculated by, you have to find, correct answer is this. Click OK. You will able to now move ahead. Go on calculating the power. Speed, then only the speed is now changed. It is now 930. And 01.78. Calculate the output power. Output input power is 220 upon 60. So torque is 2.06. 100.72. And the efficiency, it is 0.399, 39.99. Unit power, unit speed, yes. That's all about results of your trial number two. Every time when you move, before moving to next slide, you must have to take a screenshot. That is what you, every time you must have to take a screenshot of these readings once you finished and then click on the next slides. This way you have to go on conducting the trial. Individual student will conduct the trial. Minimum 5 trials you must have to conduct as I shown you for a constant head and submit your readings to me. Once you conducted your trial, then go to your post-test section. Here you have to go on answering these questions, find out the questions and find out the results. So this way you have to finish your practical number 1. I think this will be now very easy to all of you. Remember, I am going to share you the link of this link through the Google Classroom and then you will perform this experiment. Go on performing the experiment for your 5 different number of trials, obtain the results and each student must have to take a photograph or a screenshot of this. Try to conduct this. If it is not possible to conduct it on your mobile, try to have access to your uh, computer or maybe you can share with your friends also. If it is really difficult for you to conduct this virtual trial on your mobile, then what you can do, you can have some collaboration with your group of students and then even if you submitted in a group that 5 to 10 number of students are performing trial virtually and obtain their results, that is also okay. So not an issue. So that's all for your Pelton turbine trial. Of course, at the end of the practical, you have to write a conclusion that what was the aim, what you observed, what you learned from the pre-test, what you learned from the post-test, how you obtain the number of readings, what you observed in your graph. Once you conduct 5 trials, the graph will ultimately appear over the screen. What the graph is stating, that you have to state all these your learnings in your conclusion. Don't write conclusion that we find the efficiency to be 80%. I need a conclusion on every topic that what is aim, what you learn, what the theory, what important parameters that you learn from the theory understanding, what was the pre-test observations, what was the post-test observation, how you perform the various activities, and what are the outcomes of this practical, and you have to discuss that what the various graph that you plotted for Pelton turbine, what they are indicating. Don't write that there is a decrease in speed. I need that how the decrease you observe, what percentage of decrease is observed, what is your comment or reason for this decrease or reason for this increase, whatever the probability, you have to write in this conclusion context. I think that's all. We should stop now and try to conduct this practical. I'm giving 1 week time to all of you, and in this situation, you must have to submit the entire readings and outcomes of this practical. Thank you all. Go on performing. There may be a lot of questions. You may ask it at any moment. Thanks a lot. Thanks for sharing with me.